Solar energy is the most abundant permanent energy resource on Earth, and it is available for use in its direct, solar radiation form, and indirect forms, wind, biomass, hydro, ocean etc. The sun emits energy at a rate of 386 trillion kilowatts every second. Only a tiny fraction, approximately 180 trillion kilowatts, is intercepted by the Earth, or 343 watts per meter of Earth's surface, which is located about 150 million kilometers from the sun. About 60% of this amount, or 108 trillion kilowatts, reaches the surface of the Earth. The rest is reflected back into space and absorbed by the atmosphere. In a single hour, the amount of power from the sun that strikes the Earth is more than the entire world consumes in a year. To put that in numbers, each hour, 430 quintillion joules of energy from the sun hits the Earth. That's 430 with 18 zeros. In comparison, the total amount of energy that all humans use in a year is 410 quintillion joules. So, how can we capture this tremendous energy? We can capture this energy with photovoltaic solar panels. In animation, you can see how can we produce electricity from solar energy. So, how does solar panel works? On this question we will answer. First we must learn what is photoelectric effect. Silicon atom has 14 protons and 14 neutrons in his core. It has 3 orbits with electrons. Silicon has in first orbit 2 electrons, in second 8 electrons, and in third 4 electrons. To conclude, silicon is 4-valent chemical element that has a C symbol in the periodic system of element. His atomic number is 14 and his atomic mass is 28,0855. It is a member of group 14 in the periodic table, along with carbon above it and germanium, tin, and lead below. So, what is the photoelectric effect? When sun or light shines, it emits particles called photons. These photons are massless, and if photons hits one of the electrons, and if photon has enough energy, it can free the electron. As a matter of fact, it will knock it loose electron from outer orbit of silicon atom with some velocity, and in some direction. This electron become negatively charged free electron called photon electron. In electronic sheath of silicon atom a hole emerges, and whole atom of silicon become positively charged, because, after photon hits electron, in atom, we have 14 protons and 13 electrons. With simply math there is more protons who are positively charged. In terms of classical physics, when we talk about energy being conserved in this process, we can see that we have energy of the photon, energy that went in process. What happened to that energy? Part of that energy is needed to free electron. That energy we call work function. Work function is minimum energy required to knock electron from outer orbit, in our case, outer orbit of silicon atom. For silicon, work function is between 4.60 and 4.85 electron volts. And rest of the energy have gone into kinetic energy of the electron, who will become free negatively charged photoelectron after photon hits electron. It is very simple to solve this puzzle. Energy of the photon we can write like shown, where h is Planck constant 6.626 times 10 on minus 34 joules. C is speed of light, 300 million meters per second, and lambda is wavelength of the light. Work function is not the same, it depends on material. For silicon is between 4.60 and 4.85 electron volts. Kinetic energy we can write like, where 1/2 comes from integrating the equation. M is mass of object, in our case of electron, and V is velocity of object on second potential. Now, I think that we understand photoelectric effect. Solar panels absorb the sunlight as a source of energy to generate electricity or heat. A photovoltaic PV module is a packaged, connect assembly of typically 60 photovoltaic solar cells. Most commonly photovoltaic solar cell is made of this parts: N-layer silicon, phosphorus doped. P-layer silicon, boron doped. To allow electric flow of electron, metallic conductors are installed on layers. Module encapsulant, or ethylene vinyl acetate, play an important role in preventing water and dirt from infiltrating into solar modules, as well as protecting the cell by softening the shocks and vibrations to the cell. Glass and Tigler will improve the light transmittance and therefore increases the overall efficiency of the PV module. Also, it protects layers and contacts from damage. Backsheet, polyvinyl fluoride film represent optimal balance of properties for weatherability, adhesion and mechanical strength, properties that are required for long module lifetime. Now we take a look in area between N layer and P layer. I want to show you also how a silicon crystal grid is doped in N layer and in P layer. In a process called doping, impurity atoms are placed in very pure silicon to change the electrical characteristics of the crystal. Phosphorus can replace some of the silicon atoms in the crystal, and when this happens, the phosphorus atom is called a dopant atom. The dopant phosphorus atoms each form 4 covalent bonds in the same way that a silicon atom does with its neighbors. The fifth of the phosphorus bonding electrons, the one that is not used in covalent bonding, now plays an important role. This electron is only weakly attached to the phosphorus atom, so weakly that at normal temperatures the thermal energy within the crystal is sufficient to free it from the phosphorus atom. When this happens, the resulting electron is free to travel around the crystal. In typical solar cell applications, there is about 1 dopant atom for every 5 million silicon atoms. When an atom like phosphorus, with more than 4 bonding electrons, is used to dope silicon, the resulting crystal material is called N-type silicon. This is because the electrons available from the dopant atoms each have a negative electric charge. Boron, with 5 protons and 5 electrons, can also substitute in a silicon crystal where a silicon atom would normally reside. Because a boron atom has only 3 electrons available in its bonding shell, only 3 covalent bonds can be formed between a boron atom and the silicon atoms in a crystal. Without a 4th electron in the bonding shell, boron can form only 3 covalent bonds. At temperatures near absolute zero, this boron atom with its missing bond is stable. At room temperature, there is sufficient thermal energy to push a nearby electron into this hole. When this happens, the atom that supplied the electron to the boron atom now has a hole that can be filled by an electron from another atom in the crystal. In this way, hole can move from atom to atom. This can be viewed as negatively charged electrons moving around filling the holes, thereby leaving a new hole, or alternatively, simply as positive charges moving through the material, as moving holes. When an atom like boron, with fewer bonding electrons than silicon, is used to dope silicon, the resulting material is called p-type silicon. This is because these types of dopant atoms generate mobile holes in the crystal, with each hole having a positive electric charge. Doping one side of a piece of silicon with boron, a p-type dopant, and the other side with phosphorus, an n-type dopant, forms a p-n junction. The n-type material has large numbers of free electrons, negatively charged, that can move through the material. The number of positively charged phosphorus atoms, called positive ions, which are not free to move, exactly balance the number and charge of these negative free electrons. Similarly, for the p-type material, there are large numbers of free holes, positively charged, that can move through the material. Their number and positive charge is exactly counterbalanced by the number of negatively charged boron atoms, called negative ions. Now imagine that the n-type and the p-type materials are brought together. Due to the doping of the silicon crystal, there are large numbers of mobile electrons on the n-type side, but very few mobile electrons on the p-type side. Because of the random thermal motion of the free electrons, electrons from the n-type side start to diffuse into the p-type side. Similarly, due to the doping of the silicon, there are large numbers of mobile holes on the p-type side, but very few mobile holes on the n-type side. Holes in the p-type side, therefore, start to diffuse across into the n-type side. In this way it is formed p-n junction region or depletion region. Most solar cells are essentially large area p-n junctions. Now, if the electrons and holes had no electric charge, this diffusion process would eventually result in the electrons and holes being uniformly distributed throughout the entire volume. As the electrons and the n-type material diffuse across towards the p-type side, they leave behind positively charged phosphorus ions near the interface between the n and p regions. Similarly, the positive holes in the p-type region diffuse towards the n-type side and leave behind negatively charged boron ions. These fixed ions set up an electric field right at the junction between the n-type and p-type material. Free electrons and holes are influenced by this built-in electric field, with the electrons being attracted towards the positive phosphorus ions, N layer, and the holes being attracted towards the negative boron ions, P layer. So if we want to summarize this working principle in a simpler way, please follow next animation. In N layer, phosphorus doped, there is excessive electrons. N layer is negatively charged. In P layer, boron doped, there is positive charge electron holes. P layer is positively charged. Further, when two impure silicon pieces, the p-type and n-type, are brought in contact with each other, an electric field is formed. The free electrons present on the n side, seeing all the holes on the p side, rush to fill them fast. All free electrons are unable to fill the free openings. They mix successfully to form a kind of barrier, which makes it increasingly tough for electrons located on the n side to make the move to p side. The process reaches a point of equilibrium, and there exists an electric field dividing the different sides. This field serves as a kind of diode, permitting and even forcing electrons to drift from the p to the n half. Most solar cells are essentially large p-n junction area. When light shines on them, they can generate current and voltage. The reason this can happen is because of the electric field at the junction of the p-type and n-type material. If the photon energy is great enough, it can energize an electron and release it from its covalent bond. This produces an electron that is free to move and leaves behind a hole that can accept another electron. Because of the electric field, electrons are attracted towards the n-type material side. Similarly, the holes are attracted to the p-type material side. This separation of charges causes a current to flow across the junction. So, we have in n layer excessive electrons, and in p layer excessive holes. If we connect electric wire between n layer and p layer, electrons from n layer will try to fill holes in p layer, and in this way we have electric current. Now we know working principle of solar cell, and now we can put our solar panels on house roof. How to connect solar cell and solar panel you can see on picture. A photovoltaic module is a packaged, connect assembly of typically 60 photovoltaic solar cells. So we have solar panel or photovoltaic model. You can see again, construction of panel with junction box. Next, sun is shining, and solar panel is start to produce direct current. Current goes from solar panel to voltage regulator. Voltage regulator ensure that the battery is not overcharged, and to prevent reverse drain. From voltage regulator, current goes to rechargeable lead acid 12 volts battery. Then from battery it goes to inverter. Inverter increase the output voltage from a 12 volts battery direct current to 240 volts alternating current. and from inverter, alternating current powers home applications. You can also connect your solar panel to external grid to sell electricity, or you can part use for your home and rest send to external grid to sell. I hope that you enjoyed this video. Please like, share, and subscribe.